Hi, now I am going to explain the problems on Q point and load line. In the previous lecture, we studied how to draw the load line Q point and the output characteristics of transistor amplifier. In order to get this Q point in the active region, we must provide a proper biasing to the amplifier circuit. There are different kinds of biasing, fixed bias and voltage divided bias. So these two biasings we have studied in the previous lecture. In a fixed bias, if you find out Q is equal to beta IB is the 1 point, nothing but Q, ICQ, VCC minus ICRC. This point is a function of temperature. This point ICQ is a function of beta. Beta is a function of T. When temperature increases, beta increases and ICQ increases. When ICQ increases, the Q point moves. The Q point, where is initially it is a Q point. By changing the temperature and IB and beta, the Q point may move this way or this way. You will get moved. The changing of Q point in the fixed bias is the conclusion that it is insufficient for biasing network for an amplifier to get faithful amplification. That's why we go to the best model, best circuit for which is called voltage divider bias. In this voltage divider bias, we have a connection at input side, input to base region. That input network is connected as a voltage division network, and that network can be minimized, replaced with the Thevenin equivalent circuit. In this Thevenin equivalent circuit, we apply the IB at the input side. We'll get IB is equal to we have a formula for IB. Base current by applying Kirchhoff voltage law at input side, where the circuit equivalent circuit Thevenin equivalent circuit VTH RB RTH. So VCC VTH minus VBE divided by Thevenin equivalent resistance plus 1 plus beta times of RE resistor. This is the basic IB. Once we want ICQ or IC Q point, one of the Q point variable is equal to beta IB. Okay. So this is the ICQ point, and VCQ point we get VCQ is equal to VCC minus ICRC minus IERE. In order to approximately equal to IC, approximately equal to IE, we know that. So then when we substitute that one, IC, if we take IC common, IC plus RE into IC. So we have already find out IC from this input Kirchhoff voltage law. Substitute RC constant, RE constant and VCC constant, then we will get VCQ. So in order to get ICQ, VCQ will get Q point. But now this Q point is fixed or variable with the temperature or variable with some other parameters. So in order to find out this Q point, whether it is fixed or independent of beta, we will see now. The stability of voltage divider bias can be explained from the equation ICQ, where ICQ is nothing but beta DC or simply beta IB. This is the equation for IB. IB is equal to VTH minus VBE. VTH minus VBE divided by RTH plus 1 plus beta times of RE. This is called beta into IB. You will get ICQ. In this ICQ, if you analyze this equation, apply some analysis, that analysis is, when we compare with 1, beta is so large. It is far greater than 1, neglecting this one. When 1 is neglected, you will get the equation of ICQ approximately equal to beta VTH minus VBE by RTH plus beta DC RE or beta RE. So when neglecting this one, we'll get this equation. Again, we can further simplification of this ICQ equation. In order to cancel this beta, separate this beta in the denominator. When we LCM of or separate this beta in the denominator, so we'll take RE plus RTH by beta. Then we will common beta DC, and again numerator also we have a beta DC. So this beta DC, this beta is cancelled. So you will get the equation in the ICQ VTH minus VBE divided by RTH by beta plus RE. So when we assumes or when we providing a resistor, emitter resistor, in such a way that it is far greater than the ratio of Thevenin's equivalent resistance divided by beta value. Beta value is given for a particular voltage divided by circuit like 100 or anything. 100 for example. Beta is equal to 100. That RTH is equal to some value. The ratio of that RTH in some ohms or kilo ohms divided by beta 100, which will be always far less than that RE. That means RE far greater than RTH divided by beta. When it is far greater than RE, for example, it is 100K, it is only 10 ohm or some 50 ohm, some 50. So always this 10K with some value is 50 is far less than. So neglecting this term. How it is possible? By providing a large resistance at emitter resistor to get this second term neglected. When it is neglected, the total collector current IC is equal to VTH minus VBE divided by RE only. So that it is independent of beta. If it is independent of beta, then automatically the Q point on the load line is almost fixed. So when it is independent of beta, means independent of temperature. So when temperature increases, the Q point won't change, move up direction and down direction. That's why voltage divider bias is a most eligible circuit for amplification. It's most eligible for circuit for faithful amplification. So this circuit is mostly useful. This configuration, this model, voltage divider biasing arrangement for amplifier is most preferable, and it is more stable. The stability of the voltage divider bias is more, so that we can always prefer voltage divider bias. So my dear students, if you analyze in this way, when we studied CB, CE, CC, these are the different connections of transistor used in the network. When we connected these three different configurations, after studying all three configurations, we have concluded that common emitter configuration is more preferable for an amplifier. General amplification, voltage amplifier, current amplifier. So CE configuration is most preferable. Whenever we talk about amplifier, whenever we have seen any amplifier circuit, it's always configuration is common emitter only. Because after studying CB, CE, CC, we can get voltage gain, current gain, or high, and medium input resistance, medium output resistance. In this common collector, because of high input impedance, low output impedance, it will be useful for buffer or matching circuit. And this opposite of this operation, CB useful for input circuit, but C is useful for amplifier. So C configuration. Similarly, In order to get that C amplifier with a faithful amplification, which biasing we need to be preferred? We have actually four to five different kinds of biasings. Like emitter feedback bias, collector feedback bias, fixed bias, voltage divider bias. Among those all biasing networks, voltage divider bias is the preferable and eligible biasing for an amplifier because it is independent of beta. Stability is more. Okay, so the stability approximately equal to 1. So all the advantages in voltage divider bias, we can prefer fixed bias, voltage divider bias. We always prefer voltage divider bias CE configuration for an amplifier. So suppose if you see here, this is a emitter is connected to ground. Emitter is connected to ground means CE configuration. CE configuration. And which biasing is preferred? If you see this one, common emitter configuration, this is voltage divider bias network. So it is a stable circuit so that we can give faithful amplification. So whenever you want to design an amplifier, a simple amplifier, you must follow common emitter configuration and voltage divider bias circuit so that you will get faithful amplification. Now we will see some problems regarding to biasing, voltage divider bias and this fixed bias. Let us take a simple network C configuration with a fixed bias. VCC is equal to plus 12 volts and RB resistor is equal to 240. RC resistor is equal to 2.2 kilo ohms. And it is an amplifier. Just they provide capacitor 10 microfarad C1, C2 10 microfarad. For finding DC analysis, we always open circuited of these capacitors and input connected to ground. So whenever it is open circuit, no need to worry about these two capacitors, neglecting these two capacitors in order to find a DC load line. And then we have given beta is equal to 50. So find out the Q point and the load line for this fixed bias. The first idea behind this biasing circuit, how to find out load line and Q point. So find out the Q point and load line. We must apply Kirchhoff voltage law at input side, Kirchhoff voltage law at output side. To get VC Q point from the Kirchhoff voltage law at collector loop, to get IC or IB, in order to get IC, we need IB. That IB taken from input Kirchhoff voltage law. So input Kirchhoff voltage law. Now from this we can apply input Kirchhoff voltage law. Loop direction is like this. VCC, IBRB, VBE given 0.7 and no RE resistor, that is equal to 0. When we substitute this one, so that equation, when we write down that equation for this loop, then VCC minus IBRB minus VBE is equal to 0. This is the Kirchhoff voltage law applied at input loop. Then extracting the IB from this equation, VCC minus VBE divided by RB. This is the equation for IB. So when we substitute IB is equal to VCC minus VBE by RB, in this problem VCC is given 12 volts. So 12 minus VBE is 0.7 divided by RB is equal to 40 kilo ohms. So divided by 240 kilo ohm, you will get So 11.3 divided by 240 into 10 to the power of minus 3. So we'll get a 47.08 microampere. 47.08 microampere. Once we have this 47 microampere for IB, we know the equation ICQ is equal to beta IB. ICQ is equal to beta IB. Beta is equal to 50 given, and IC already we find 47.08 microampere. Multiply with this beta 50, you will get 2.35 milliampere. IC always measured in milli, IB is always measured in microampere. VCQ is equal to it is measured from Kirchhoff voltage law across collector loop. So VCQ is equal to VCC minus ICRC is equal to VCC minus ICRC. It is a loop VCC, ICRC, VCE is equal to 0, so that we can get this VCQ is equal to VCC minus ICRC. VCC is the 12 volts, is fixed, and then IC 2.35 we derived, we find from this equation, and RC 2.2 kilo ohm. So when we substitute 12 minus 2.35 into 2.2 kilo ohm, we'll get 6.83. So here, what is the Q point? Q point is equal to, here Q is equal to 2.35. What is ICQ? 2.35 milliampere, comma, what is VCQ? 6.83 volts. This is called Q point. So in this problem, they asked Q point in the fixed bias transistor. If you want to draw the Q point on the output characteristics, we must know the load line. How to find out load line? It's very simple. Load line, take this output equation, Kirchhoff voltage law, VCQ is equal to VCC minus ICRC. Substitute x-axis variable to get the maximum point on the y-axis, which is called IC sat. Substitute y-axis point, will get the maximum point on the x-axis, which is called VC cutoff. So we draw the load line. What is the x-axis point 0 in this equation? X-axis point nothing but VCQ. When VCQ is 0, IC is equal to VCC by RC. So in this case, IC is equal to VCC by RC means VCC is the 12 volts. 12 divided by, and then RC is equal to 2.2 kilo ohm into 10 to the power of minus 3. So 2.2 approximately equal to 6, around 6, for example, it is 6 milliamp. 6 milliampere, approximately equal to 6 milliampere. This is the maximum point, IC sat. Then what is VC sat? By substituting IC is equal to 0, we'll get VCQ is equal to VCC. So VCQ is equal to VCC. What is VCC? 12 volts. So maximum point VC cutoff is equal to 12 volts. Maximum point on the y-axis is 6 milliampere. When we join together 6 volt and 12, and in this load line, this is called load line. In this load line, we can get the ICQ and VCQ point. ICQ, where it's ICQ 2.35. It is entire 6, maximum 6. So about 2.3 means around this one. So this is the joint line. and corresponding voltage nothing but 6.83 volts, 2.35 milliampere. So this is called Q point. In the examination, if they ask this, find out the Q point and load line, or find out the Q point for this fixed bias network, you have to find out, apply the Kirchhoff voltage law at input side to get IB, and then find out the IC by multiplying beta. Beta IB is equal to IC, which is one of the variable, and then apply the Kirchhoff voltage at output loop. You will get VCQ, and apply the load line by substituting X variable to get the Y point, by substituting Y variable to get the X point, and join the load line and draw the Q point for this particular problem. The Q point is 2.35 milliampere, 6.83 volts. So in this way, you need to find out the Q point and load line for this type of biasing networks. If you see another problem regarding to voltage divider bias. Voltage divider bias network having a transistor with the RC resistor and RE resistor, and input biasing base bias which consists of R1 in parallel with R2 in a network like voltage division, follow voltage division rule. So in this type of network, there will be R1, R2, RC, RE. This network is called voltage divider bias network. For this network, we need to find out Q point and load line. If you want to find out Q point and load line for this, we must convert this network. This VCC, R1 and R2 network can be replaced with the Thevenin's equivalent diagram. When we replace Thevenin's equivalent diagram, then only it is possible to find out input Kirchhoff voltage law and ICQ. So this is the separate separate the voltage division network by providing same VCC. So R1 and R2. This network are equivalent to VTH and RTH. In the previous lecture, we have seen that how to find out with VTH. A voltage drop across the R2 resistor is called VTH. And by shortening the voltage source shortening the voltage source and looking into R2 resistor, what is the equivalent total resistance for the network is called RTH. So VTH is nothing but total voltage VCC into multiplied by voltage across that resistor R2 divided by R1 plus R2. When we substitute the values, what is VCC here in this problem? The VCC is 10 volts. When we substitute VCC 10 volts, 10 volt, 10 into what is R2? R2 is equal to 5.6, R1 is equal to 10 kilo ohm. So R2 is equal to 5.6 kilo, and in the denominator R1 is equal to 10 kilo plus 5.6 kilo, 15.6 kilo. 15.6 kilo, and here it is kilo. Just both are cancelled. You will get 5.6 divided by 15.6. You will get 3.59 volts. This is what Thevenin's volt, the voltage across base terminal, voltage across R2 terminal. When we have given 10 volts to the VCC, we have got voltage divider, dividing the voltage and available across the base point with respect to ground or R2. We'll get 3.59, almost 3.6. So then we have to see that RTH by simply blindly remember that R1 and R2 are parallel. By looking resistance through the R2, this network, they are two are in parallel, that R1 parallel R2, nothing but total RTH resistance. RTH is equal to R1 parallel R2, nothing but R1 R2 by R1 plus R2. R1 10 into 5.6, nothing but 56 kilo ohm square, 56 kilo square divided by 15.6, 10 plus 5.6 kilo, 1 kilo cancel, and then we'll get 56 divided by 15.6. 56 into kilo divided by 15.6 will get 3.59 kilo ohms. When substitute this we have RTH, we have VTH now. So apply the Kirchhoff voltage law. When we apply Kirchhoff voltage law to this network, VTH minus IBRB minus VBE minus IARE, then you will get IB here. IB is equal to VTH minus VBE divided by RTH plus 1 plus beta times of RE. All the parameters we have in the problem. VTH 3.59 we got. VBE is the 0.7 voltage across between base to emitter voltage, and RTH is the 3.59. This 3.59 plus beta is already given in the problem. Beta is 100. So this 100 is substitute here. Beta 100 plus 150 multiplied by RE 150 ohms, which we will be calculate through calculator. So we'll get 48.046, 48 microampere. 48 microampere we got from input Kirchhoff voltage law, which is equal to IB. Once we have IB, IC is equal to beta IB. So we find out this IB from this one. So beta IB, nothing but beta 100. IB already calculated 48.046, nothing but 48 microampere. Multiplied here, we'll get 4.8 milliampere. So this point move this way, so that this is multiplied 0, 3 zeros cancel, 4.8 milliampere. So IC is equal to 4.805 milliampere. VCQ is equal to, according to this network, this output loop. So VCC minus ICRC minus VCE minus IARE is equal to 0. Then we'll get VCQ is equal to VCC minus IC, RC plus RE plus IC, RC plus RE, ICQ nothing but substitute IC approximately equal to IE. When substitute IE in the place of IE, I substitute IC, we'll get RC plus RE into ICQ. We have already derived and find out the ICQ. 10 minus RC 1 kilo, RE 150, 160 ohm, and ICQ 4.8 milliampere, you will get 2.50 volts. This is what Q point. Q point is equal to that ICQ nothing but 4.8 milliampere, comma 2.5 volts. When we draw the load line, so for this voltage divider bias network, we'll draw the load line. The load line IC versus VC graph. When we substitute in this equation, what is y-axis variable 0? IC 0, for example, this one is 0. So VC is equal to VCC, which is equal to 10 volts. 10 volts in the VC graph. And then what is the maximum point on the x-axis, y-axis? Substitute x-axis variable 0. When it is 0, 0 is equal to VCC minus RC plus RE into ICQ. ICQ is equal to VCC, ICQ is equal to VCC divided by RC plus RE. So VCC 10 divided by RC plus RE. So here RC plus RE, RC is equal to 1 kilo 5.560 ohms, approximately equal to 1 kilo and 560 ohm, 0.5 kilo, 1.5 kilo. 1.5 kilo means you will get 5.6 or 6 something. 5.6 or 6 something. So ICQ is equal to 5.6 milliampere, and join these together, we'll get load line. It is called load line. In this load line, we got ICQ point 4.8 milliampere and corresponding voltage 2.5 volts. Draw the Q point. This is called Q point. So for this problem, we got Q point and a load line. So in this, if you observe here, if it is fixed bias, for example, if I am changing this beta, I am not changing. This beta is functions of temperature. Due to temperature, this 50 is varied to 100. If it is 100, when it is multiplied 100, then if it is multiplied 100, so we'll get 4.7 milliampere. We'll get 4.7 milliampere. Where is the 4.7 milliampere? This is almost 4.7 milliampere. When it is 4.7 milliampere, this Q point move to this place. When it is Q point move to this place, then earlier complete faithful of the signal. When it is this is a Q point, then automatically this signal is clipped off. So when this Q point move to saturation, near to saturation, so by changing the temperature, beta value changes. If beta value changes, then Q point changes. This unfaithful amplification signal gets cut off, so that we can get this beta is independent of temperature, and this beta is independent. This voltage divider bias network independent of beta in the voltage divider bias network. So in this voltage divider bias network, if you choose this 560 ohm RE resistor is choose in such a way that RE resistor is far greater than RTH by beta, then for example it is 560 kilo ohm, not 560, at least 50 kilo ohm. If you take 50 kilo ohm, the entire equation ICQ is equal to, it is independent of beta, VTH minus VBE by RE only. Okay, so you will get the independent of beta. The Q point won't change. In order to get this one, we have analyzed that choosing the RE resistor is far greater than RTH by beta, so that in the examination they will ask voltage divider bias network and finding the load line and Q point, and they have given parameters RE, RC, R1 and R2, beta value, VBE. If it is not mentioned in the beta VBE value, we by default we take 0.7 volts, and then finding the Q point and load line for the biasing circuits. So this is called DC load line and the Q point. It is most important thing to keep that Q point in the active region, and in order to get that Q point in the active region for a particular network, we follow the load line analysis by taking the load line for a particular network and then finding the Q point in the load line by cross section of output characteristics and load line, so that we can get the Q point. In this way, we'll get whether the particular given circuit is faithful amplification or not is checked by the load line and Q point for the particular circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.